Okay, so today we're going to learn about ionic compounds again, of course. We're going to talk about solubility, conductivity, pH, and state of these compounds. We're going to predict whether ionic compounds are relatively soluble in water using a solubility chart, so how well they dissolve in water. This is going to be important for your lab, so that definitely want to make sure that you understand what these properties are, and if you're not sure, make sure you ask. But we will go through this, and then we'll do molecular probably tomorrow, looks like, and we'll do that tomorrow, and then we'll do some acids and bases as well. So between those four things, that's kind of your first lab, what it's going to be based on: ionic compounds, molecular compounds, acids, and bases. All right. So I think you got to fill in a few things here. Identifying ionic compounds, of course, ionic compounds always contain cations, which are positive ions, and anions, which are negative ions. The cation will either be a metal ion or the ammonium ion. And of course, you can recognize an ionic compound quite quickly by its formula. Okay. So cations, of course, we know as positive ions, usually a metal, obviously, or this ammonium one, NH41 plus, that's in the top left there, polyatomic ion. Next part, okay. They have very high melting points. Now, this would be hard to test in the lab because we need incredible heat to do this. High melting points. So ionic compounds have a high melting point, and so all are solids at room temperature. So remember this. When we go to the lab on whatever day we go here, the first thing is that they're solids at room temperature. So no matter what, all ionic compounds are solids, right? The cations and anions are strongly attracted to one another. It takes a large amount of energy or heat to separate them from one another so they can enter the liquid state. In a solid, all the particles are closer together than they are in a liquid, of course. So they're all bounded together here. So these, like I said, ionic compounds are always going to be in a solid state. That doesn't mean that it has to be ionic. I'm just saying if it's a solid state, there's a chance it's going to be ionic. Some molecular compounds are in solid states as well, but ionic compounds always are in solid states at room temperature. Okay, if you go into the back room, we probably have about 250, 300 different ionic compounds back there, and they're all solids. Okay, they have to be. That positive negative attraction holds together really well, and it takes a lot of energy to break that. All right. I'm not sure if it's here, right here, for example. Don't worry about this too much. I really don't care about like the charges stuff, but look at those. These are the melting points of these compounds, the melting points. All right. So when they turn from a solid to a liquid, look, sodium chloride. Sodium chloride melts at 801 Celsius. All right. So obviously, like I said, we're not going to do this in the lab because 800 Celsius would be like what? That's like 4 ovens basically, yes, put together. So you know when you're cooking your mini pizzas at home, right? Marcus, right? So you're cooking your pizzas at home, all 5 of them. Yeah. And you're sticking, you know, you stick the pizza in the oven. That's 400 Fahrenheit, roughly-ish, somewhere in there. That's about 200 Celsius. And you know, when you open up the oven door and you stick your head in to grab the pizza, you know how hot it is, right? That's 200 Celsius, roughly. This is 800, all right? So quite a bit. And then MgO, as we know, magnesium oxide, is 2,800 Celsius, all right? That's a lot of energy, right? So that, I don't even know how to explain that to you. That's just really hot, all right? The reason that they have, part of this is the reason they have these different melting points is the more electrons you gain and lose, basically, the better they stick together. And the better they stick together, the higher the melting point's going to be. All right. So if you think about the charges here, you think, okay, this is a 1 plus and a 1 minus. Okay. This is a 2 plus and a 2 minus. So it technically just sticks together a little bit better. That's all. All right. We don't need to worry about that too much. All right. I guess you can write that down because they say, why is there a large difference between the melting point of NaCl and MgO? You can just say, based on their charges. Good enough. Okay. All right. No. All right. So just a quick little idea here. Just remember the solids are all jammed together. Okay, so if you're looking at a solid, this is what it would look like on an atomic level. Okay, they're all jammed together. There's no freedom of motion here. Basically, they're all jammed together and they're all linked to one another. Here we have the liquid form. There's a little bit of space in between them. So in liquid form, we get a little bit of space, and some particles are allowed to slide past each other. That's kind of what water does, of course. And then gases, you know, mostly empty space, and we have some particles in them, but they're pretty much free from one another. All right. You need to copy this, I guess. In the space below, it says right above retention of the crystal shape there. It says in the space below, sketch the appearance of solid, liquid, and gas. You don't have to draw like 500 particles here, obviously. Please don't, because it'll take you forever. But you kind of get an idea there. Another. Next. So retention of the crystal shape. Ionic compounds have what we call a crystal shape, sometimes called a crystal lattice, with flat surfaces. When the crystal is hit, like charges will start to line up with one another, and they will start to repel each other. And when that happens, the crystal splits apart, producing a new flat surface. Right? So you guys can go ahead and draw that there. Space below, sketch what this looks like. So go ahead and draw that there. Just like it to record. When you do hit these ionic compounds, they tend to shift, basically, instead of plus, minus, plus, minus, plus, minus, nicely arranged kind of thing. They become, like charges will become aligned. And once enough like charges become aligned, and we're talking like millions and billions probably, and even more than that, once enough of those like charges become aligned, they will tend to break in a smooth, well, we say line basically, but technically they're three-dimensional, so smooth plane. So they kind of break in a smooth, it'd be like taking a cube and then kind of just cutting it in half kind of thing. You get two cubes kind of thing. All right, so that's what will happen here, because like I said, we're shifting these down, and then the pluses, these two pluses will line up, these two, and then these two, et cetera, et cetera. And if enough of those line up, like they do there, for example, in the repulsion, they repel each other, they'll break in that smooth line. So that's a pretty common characteristic of ionic compounds. Obviously kind of hard to see at times, so we have to be aware of that. All right. Next, there's a crystal shape, so that's kind of what some look like or may look like, just so you kind of have an idea. Right. Now, just a quick little review here. We know that there's two parts to solubility, yes? There is the solid that we're trying to dissolve, or it doesn't have to be a solid technique, it could be a liquid or a gas, but there's that substance we're trying to dissolve. We call that the solute, all right? And then in most cases, we have something that tries to dissolve that or tries to break that up, which in most cases for us is water, and that would be the solvent, right? If we're talking about water as the solvent, we talk about something called aqueous solutions. Have you heard that before? Aqueous? Yes? No? Yeah, aqueous. All right. So if sugar is dissolved in water, what's the solute? Sugar. What's the solvent? Water. Okay. So that would be an example of that there. Okay. So just a reminder there. Now, the solubility in water here, so we're on to this part here. It says here, all ionic compounds dissolve in water to some extent. Cations and anions are attracted to water molecules because each water molecule is polar. Water is polar because the hydrogen has a slight positive charge and the oxygen has a slight negative charge. Okay, so I'll let you guys fill in a few things there. Actually, probably need to fill in the rest of that page there now, don't we? Okay, so think about the things we. So there's an example of sodium chloride and water, and this is basically what happens. So this would be our solid form here, of course. Okay, This is our solid form here. And we put sodium chloride into water, or basically salt. You know what, you've probably done this at home when you're cooking noodles. When you put this into water, what happens is the water molecules have a little bit of a negative and positive charge, and it pulls this ionic compound apart. So the negative, for example, the positive ends here, these would be the hydrogens right here. So this is the hydrogen here and here, and they would pull that chloride closer to them, okay? And in another case, perhaps the negative end of water, okay, this right here, this negative end, is attracted to the sodium ion, for example, all right? So basically what happens is water's polar, and it pulls this ionic compound apart. Now, some ionic compounds come apart fairly easily, okay, which we're going to learn here, and some do not. Some tend to stick together, and it's very hard for water to break them apart. It just depends on how well they stick together, all right? But that's kind of, you have that in your notes there in the bottom there, and that's kind of just a little representation of what's going on with sodium chloride when you put it into water. Those water molecules help break up that ionic compound, okay? Next, I guess we're on to what? Conductivity, is that correct? All right, so solubility is definitely a part of ionic compounds, how well they break up and how well they don't. So we need to keep that in mind. Conductivity is a big one for us. If we put a conductivity meter, have you used a conductivity meter before? Yes, no, anyone? Okay, well, we'll learn that. Conductivity meters will measure basically how many ions there is and how well that solution can conduct electricity, all right? So solutions containing ionic compounds are good conductors of electricity, unlike pure water, which has almost no conductivity, all right? So ionic compounds in water tend to be very good conductors of electricity. So conductivity in solution, we're on the back page here, by the way. Solutions containing ionic compounds are good conductors of electricity. When you put them into water, they tend to break up to some extent. We're going to talk about that a little bit, but they will conduct electricity in some way, shape, or form. Now, they might be not great conductors, and they might be very, very good conductors, but they will always conduct electricity, all right? Sometimes we call those electrolytes in some cases, but they will always conduct electrical current to some degree, okay? The greater the concentration of ions in the solution, the more conductive it is, so the more you put in, okay? If you just take one little grain of salt and dump it into water, you'll get a little bit of conductivity, but if you take the whole bottle and dump it in, okay, we should get a lot of conductivity because we're going to have a lot more ions, of course. All right. So solutions of ionic compounds are excellent electrolytes, which means a solution that can conduct electricity. That's what electrolytes is. If a solution does not contain ions, for example, sugar water, it should not conduct electricity. The dissolved ions are free to move and carry a charge. I'll let you copy that wherever you need to there. Here we go. So we're going to learn how to basically decide which ones break up very well, which ones don't, and we'll need a periodic table for that, which we'll talk about in a second here. But some ionic compounds will be very soluble in water, while others are only what we call slightly soluble. Here's the two key terms that you need to know: very soluble and slightly soluble. All right, very soluble and slightly soluble. If a compound is only slightly soluble, so if it is slightly soluble, we may get a precipitate may form. That's another key term that we probably need to know. And that is a solid with low solubility that usually forms from a solution. To determine if an ionic compound is soluble, we can use a solubility chart, which we're going to do shortly here. All right. There is some steps in order to determine this, and this is kind of an important part of chemistry. So we definitely need to be able to do that. Using a solubility chart. I'm going to let you copy these 4 things here. So we'll talk about that, and then we'll go through some examples together to decide how we're going to actually go ahead and do that. Well, we're going to review anyway, but so we're going to have solubility periodic tables out. We're actually going to flip them over to the back side, and we're going to look at the top top right for you. Okay, that is our solubility chart. We are going to find the negative ion, okay, in the top row of the table, And then we're going to look for the cation and decide if it's very soluble or slightly soluble, and that'll kind of decide what kind of compound we have here. So we have some examples here, so we'll do that. Let's see here. What's our first one? Our first one's aluminum sulfate, yes? You know what, I think we're going to skip this part here, and let's go to right here. So just to kind of keep pace with you here. Give me 1 second here, because I need to find my periodic table as well here. So like you, I have this data booklet here. This is where your stuff comes from, of course. It is right. And again, this is in Google Classroom, I believe. That's what you have there, yes? Okay. So when we're looking at these compounds, we're going to start with the negative ion across the top. And across the top, that's what they're talking about right here. Notice that most of these are negatively charged. There's one positive one there. Don't worry about that too much. But we're going to start with the negative ion across the top. All right. So if you look here, this is nitrate and chlorate and perchlorate and acetate, F minus, and then there's a whole bunch over here, of course. And that's what we're going to look for first across the top. All right. Then we're going to look for the positive ion in either this row here or this row here. And that's going to determine whether it's very soluble, which it says right here, very soluble. If it says very soluble, we're going to put an AQ there. And if you want, you can write that on your periodic table there. That means aqueous, all right? So if it's very soluble, we call it aqueous, very soluble. If it's slightly soluble, if you remember from the notes, it said if it's slightly soluble, we're probably going to be form some kind of precipitate, which basically means it's going to form some kind of solid in the solution. So we're going to put actually here, solid. Now remember, it doesn't matter which one we're talking about here, whether it's very soluble or slightly soluble, or aqueous solid, same thing. What matters is we're always going to get some free ions in these solutions. So there's always going to be some free ions, but these would tend to combine together to form a solid, the ones on the bottom. So you'd probably see that form, okay? We'll do a little review here one of these days for that when the time comes here, okay? All right, so let's go back to here for a second. So the first thing we're going to do here with this one is we're going to write out the formulas for a little practice for formulas. So there's 4 compounds there. Why don't you go ahead and do that real quick? Write out those 4 compounds as good practice for tomorrow. You're going to get a little more practice today on ionic compounds, of course. So that's going to be our goal today. And then that'll help you for the quiz tomorrow as well. So we'll go over this homework tomorrow before we have our quiz. Just one last kick at the old ionic compound naming thing. But go ahead and write the formulas for these 4 compounds. You go ahead and do that. I'm going to do it up here as well. And just a reminder, maybe sometimes in some cases, like I see she's doing right now, you know, if you want to write out the 2 ions, that's not a bad thing, because that might even help you with this particular one, because aluminum sulfate, of course, this would be a 3+, right? And this is a SO4 2-. Those are the 2 ions we're really interested in when we're talking about solubility, right? We have a positive ion and a negative ion. Of course, we need to combine those 2 together, but that's where we get this formula here, right? Aluminum sulfate, swap and drop, yes, brackets appropriately, and so on, okay? I guess, you know what, while I'm on this one, here's what we're going to do. So I need you to go, whether you're there or not right now, if you're looking at the other ones, just maybe stop. I'm going to change my mind here a little bit. Let's go to the backside, to this solubility chart. And here's what we're going to do. We always look for the negative ion across the top. So we're going to look for, of course, sulfate. Yes, that's my negative ion, SO4 2-. There it is right there, SO4 2-. So I find that across the top. Where does aluminum 3+ fit? Does it fit in this most category right here? There's most, okay? Or is it one of the ones listed down here? Do you see aluminum 3+ anywhere here? Anywhere there? No. So if it's not down here, it's not there, it has to be in the other part, yes? So it has to be in the most category. Most of the ions with sulfate are very soluble, yes? Aluminum 3 plus fits into that in most category. I know that because it's not one of the ones listed down here, so aluminum 3 plus must be here. Yes? Okay, I'm only focusing on that one ion. I don't care about anything else. And because it's in this row, that means it's very soluble. So when it says very soluble, we're going to go back to here, and we're going to say AQ is what we're going to put behind it. That means, that implies that it's very soluble. If you took aluminum sulfate and you put it into water, it would probably dissolve fairly well. Okay? In fact, probably to the point, if you ever took sodium chloride and put it in water, it disappears, yes? It's like magic. Well, that's probably what would happen with aluminum sulfate as well. Okay? We'll do this one here just for time's sake. Calcium 2 plus oxalate looks like this. So 2 plus, 2 minus, swap, drop, and reduce. Yes. 2 plus, 2 minus. All right. Yes? Okay. 2 plus, 2 minus, swap, drop, reduce. Right? So we're doing with the calcium ion and the oxalate ion. Let's go ahead and find this oxalate ion right here. Uh-oh. Uh-oh. Let me guess. So let me get rid of some of this stuff here. Is this going to work? No. Oh, yeah, it does. Sorry, just give me 1 second here. So if we find oxalate across the top, OOCCOO2 minus, yes, that's right here now. So there's my oxalate ion, and I have to find calcium 2 plus. So I look down here, and I say, okay, now you have to be a little careful. This is group 1 ions, yes? So group 1 ions would include things like in group 1, lithium, sodium, potassium, rubidium, cesium, francium. Okay, it's not that, so we don't have to worry about that. Here's NH4 1 plus. This is a very specific one, so they're saying that cobalt 2 iodate is actually soluble. If it was cobalt 2 oxalate, then it would be down here. These are kind of 2 exceptions to the rule, and I think what I'll do is I'll leave those for now, and we'll talk a little bit more about that tomorrow because we're kind of running out of time today. But for the most part, they kind of fit into these nice things here. If we're looking for calcium, did you see calcium anywhere there so far? Calcium 2 plus? So if it's not here, it has to be down here, yes? So calcium 2 plus and oxalate would probably form what we call as slightly soluble, okay? Because calcium 2 plus would be here, therefore it's in this slightly soluble row, yes? And of course, we know that slightly soluble, we're going to use an S to indicate that for solid or precipitate. So we're going to go back to here, and of course, if this would work, right here, behind here, I'd put an S, yes? Okay, so put an S right here behind calcium oxalate.